Apologize for the interruption. The phone rang. Back to the lecture. So the second is 2 true, 2 false, 2 true, 2 false. The third one is true, false, true, false, true, false, true, false. Now, let's look at asymmetric B. We are looking for true when exactly one of these two entries is true. So that would mean this third row is true. The fourth row is true. The fifth row is true. And the sixth row is true. In the first two rows, both are true, which means the symmetric difference is false. In the last two rows, both are false. Both are false. That means the symmetric difference is false. Okay. Now for B symmetric difference C, again, we are looking for true when exactly one of these two is true. So here in the second row, X is a member of B symmetric difference C. In the third row, exactly one of them is true. In the sixth row, exactly one of them is true. In the seventh row, exactly one of them is true. In the other rows, here in the first row, both of them are true, which makes X's in B symmetric difference C false. In the fourth row, both of them are false, which makes X's in B symmetric difference C false. In the fifth row, both of them are true. In the eighth row, both of them are false. Either of those situations makes X's in B symmetric difference C false. So now we look at asymmetric difference B in parenthesis, symmetric difference C. We're looking for exactly one of these two columns to have a true in it. So that would be here, not here because they're both true, here, not here because they're both true, but here, and here. Not here because they're both false. So true, false, false, true, false, true, true, false. Now, in the last column, we are looking for A symmetric difference, B symmetric difference, C in parenthesis. So we want exactly one of these entries and these entries to be true. So here we've got a true with a false, which is a true. Here we've got in the second row a true with a true, which is false. In the third row, we have a true with a true, which is false. In the fourth row, we have a true with a false, which is true. In the fifth row, we have a false with a false, which is false. In the sixth row, we have a false with a true, which is true. In the seventh row, we have a false with the true, which is true. And in the eighth row, we have a false with a false, which is false. So now again, we look, do they match? Both true, both false, both false, both true, both false, both true, both true, both false. So they match. This truth table shows that X is a member of A symmetric B symmetric C is logically equivalent to X is a member of A symmetric B symmetric C. Therefore, by definition of set quality, we may conclude that the set A symmetric difference B, symmetric difference C equals the set A symmetric difference B symmetric difference C in parentheses. This is showing that the operation of symmetric difference is indeed associative. And that ends our proof. Okay, we have now shown that the symmetric difference is both commutative and associative. We will show that it is well defined next. Stay tuned.